The purpose of this project is to accurately launch a tortilla in a repeatable way. Our customer is Tacos El Robert, and the end usage for the Tortillapult is to transport tortillas across their serving floor without creating additional walking traffic. A prototype Tortillapult is created and used to measure the distance and the force of the launcher. The average spring coefficient is determined using mechanical force gauge to compare distance displaced by force applied. Distance launched and other geometric constraints are taken using a tape measure. The performance of the prototype Tortillapult is determined to be unacceptable. With a 95% confidence, the distance launched as a function of force is given right here, with plus or minus 2.9 feet uncertainty. This is unsuitable for use in Tacos El Robert. The Tortillapult is to be used in Tacos El Robert as a way of reducing the walking traffic and decreasing the wait time for tortilla distribution. The purpose is to create a Tortillapult that can repeatedly launch a tortilla between 4 to 13 feet onto a 4-foot table with a 95% confidence for Tacos El Robert. It will be mounted in a central position with a 180-degree horizontal rotation and adjustable force so that all tables within the target range are reached. The Tortillapult must be no larger than 2.5 feet in any direction. The two problems that Robert wants the Tortillapult to solve are the needed force to reach a table at a specific distance and the confidence that the tortilla will reach the table. Using large quantities of rubber bands allows for low uncertainty, which meets the good enough design requirement. If the Tortillapult can successfully supply 19 out of 20 tortillas to a table, Robert will be happy. The main requirement for this design is that there is a simple correlation between the applied force and the distance traveled using rubber bands. Future prototypes may consider alternate approaches. The Tortillapult is made of wood and other eco-friendly materials, and it uses a disinfectable polymer launcher that allows Tacos El Robert to maintain proper food safety. No other factors are needed to be considered for responsible design.
The major components of the launcher are listed. The first one is the launcher and the moment arm. We chose to go with this because it has a consistent launch length and decreases variables, as the only variable is the amount of rubber bands. Practicality is the reason for this improvement. The assumptions, alternatives, and results are listed below. The next major component is the guide rails. We chose to include the guide rails to ensure a straight trajectory of the lever arm. The addition of friction bias error is minimized in the calibration process. This bias error is justified by the elimination of accuracy error. Precision was the reason for this adjustment. The assumptions, alternatives, and results are listed below. The next major component is the tortilla holder. The launcher tortilla holder has curved edges to hold the tortilla flush against its surface. It has extending surfaces on the back to be bolted to the moment arm. This secures a good enough placement area. The assumptions, alternatives, and results are listed below. So the next major component is the rubber band spring. We chose rubber bands because they retain the desired elasticity over repeated testing. The assumptions and alternatives are listed below. The results, the rubber band did not elongate significantly and produce consistent results. Since they are standard size and easily replaceable, the bands meet the good enough requirement. The next major component was the angled rubber bands. The angled rubber bands increase the stability of the launcher arm. The force average is in line with the launcher arm but includes additional horizontal support. The assumptions and alternatives are listed. The results, the moment arm remained stable throughout the launch process and testing procedures and met the good enough requirement.
The Tortillapult testing will be done in a large open area for safety purposes. We'll be weighing down the Tortillapult to prevent any breakage or accidents happening, and the operator of the Tortillapult will announce before the launch happens to ensure that people are paying attention. The key variables in this design are the amount of rubber bands contributing to the spring force, the moment arm length, and the distance the tortilla travels. The control variables are the rubber bands and the moment arm length. The moment arm length was chosen to be fixed at 30 inches, and the rubber bands had a base force of 22.25 pounds per inch due to the stabilizer bands, and the additional units adding approximately 12 pounds per inch per unit added. The key variable of force is controlled by adding 10 rubber bands per unit. The uncertainty of the force provided by the spring was found to be this, with the uncertainty being plus or minus 1/32 of an inch on distance. The distance measure was done by attaching a end of the tape measure to the base of the Tortillapult and measuring to the close part of the tortilla. The projectiles would occasionally bounce or slide, which was okay, but when the projectiles rolled and added an increased distance, they were removed because they were outliers at that point due to the unusual landing position. The major equipment that is used was the launcher and the mechanical force gauge. The tortilla launcher was pulled back with caution when all people are out of the path of motion. The force gauge was used horizontally to avoid calculating for gravity, and a calibration curve has been obtained, which will be gone over in the appendix. A circular table was used in the testing to represent the tables at Tacos El Robert, and our goal is 95% of the tortillas to land on that table to meet the design requirements. The tortilla is loaded onto the launcher as pictured. The launch pin was inserted, announced that it would be launched, and then the pin was pulled and it was launched. The uncertainty of the calculations came from the mechanical force gauge and the tape measure used to measure the rubber band force and distance traveled.
The Tortillapult was able to launch tortillas 12.8 within about 2.9 feet with 95% confidence and an applied spring force of 92.2 pounds. Theoretically, it should have been able to launch tortillas 11.2 within almost 4 feet with an applied spring force of just 45.6 pounds. As you can see, the observed and theoretical launch distances were pretty close at low applied forces, but diverged at high applied forces. This is because the major weakness in the theoretical estimate is air resistance. It assumes no air resistance or friction in the Tortillapult unit. Also, the applied force is estimated based on maximum stretch length of the rubber bands, and the angle of the diagonal rubber bands stays the same as the arm moves. A weakness in data collection is that we only measured a straight line distance instead of any spread laterally. This is the calibration curve that we obtained. We obtained it by doing students' T distribution analysis on 8 launches per spring force condition. And And this is how we measured those distances, as mentioned in the methods section with a tape measure from a single specific point. This is a distribution of spring constants of the rubber bands. And uncertainty in that mainly comes from the limitations of resolution from the spring force gauge and the ruler.
The statistical tools used in the analysis of the results were Gaussian sample statistics for 30 samples taken of the spring constant for the rubber band, sample T sample statistics for each tortilla launch configuration. 8 samples were taken of each band configuration, and this is covered more in depth in the appendix. Another tool that was used was the uncertainty propagation, and this was calculated through all the theoretical equations. That shows the uncertainty of each of the measured values, and you can look in the appendix for in-depth calculations. And overall, we were able to reach the launch distance goal of using 60 rubber bands, which corresponds to an applied load of 92.2 pound-force. Yet associated uncertainty at 95% confidence is about 3 foot. This interval is not adequate to accurately land tortillas on a 4-foot table, as was the goal.
In conclusion, our results were already mentioned, but we were able to launch almost 13 feet with 92 pounds, should have been able to launch 11 feet with just 46 pounds. Now, the spread on these is too great to achieve our original goal of landing tortillas with 95% confidence on a 4-foot table. Experimental results were obtained as described in the methods section and a little bit in the results. Ben got our theoretical results for us, and they are in the appendix. Now, the requirement was not met, which means Robert is not going to be able to use this in these dining areas as originally intended. As an alternative solution, we can launch tortillas onto a 6-foot table with greater accuracy. Now, neglecting air resistance and treating the tortillas as a point mass contributed the most to our unmet constraints, and this can be improved by including air resistance and even doing some numerical CFD analysis on it. Now, for future models, the Tortillapult should be firmly anchored to the table or ground, so increase repeatability and safety. And also, you could launch stacks or packets of tortillas instead of individual tortillas, because they will act more as a point mass instead of a flat plate with very little mass. Future designs could also include an adjustable incline of the entire Tortillapult, because that would allow more fine-tuning of the launch angle and where you want it to go.
The uncertainty analysis appendix is as follows. First, we use precision and systematic errors. The precision errors in our project refer to the inconsistency of the results in the variance. For example, the standard deviation of the K-values in rubber bands. A systematic error refers to the variance of the measurement due to the accuracy of the device. For example, the force gauge is an uncertainty of 0.25 pound-force. The Gaussian statistical analysis of the rubber band spring constant yielded the following results. This at a 95% confidence interval. The following is the uncertainty analysis, and this is the raw data. The student T statistical analysis of the flight distance of the tortilla is shown. Only 8 samples were taken of each, and so we're 95% confident that all of the launches at any configuration will land in this range. And the uncertainty analysis for the major variables, velocity, distance, and time, we already showed the ones for K, are as follows. It propagates through all these formulas using an accurate uncertainty analysis, yielding that. And for the hypothesis testing, we used a hypothesis testing of our confidence interval being less than 2 feet. That was our null hypothesis. And we hypothesized that our confidence interval was less than that 2 feet. After a full confidence interval analysis, we determined that we reject the null hypothesis and our uncertainty is greater than 2.9 feet. Finally, the uncertainty analysis appendix is shown here for the uncertainty analysis chi-squared goodness fit test. And this is for the calibration of the launcher. We use the least square root residuals in order to get this line and the following uncertainty. And finally, we have the uncertainty of instrument performance for the following instruments that we use, and the theoretical values and uncertainties for the following theoretical versus actual flight paths, distances, and times.
Alternatives to the designs that we have are listed here. The launch arm. An alternative to the launch arm is to launch the tortilla sideways instead of launching it straight as we have to reduce the area. A variable length launch arm would incorporate different positions for the tortilla holder to go to launch at different lengths and vary the distance traveled. Alternative to the guide rails. No guide rails could be used, or tighter tolerances on the launcher arm and the pivot could be used. Instead of rubber band springs, metal springs could be used, or thick elastics could be used. Instead of angled rubber bands, all rubber bands could be running parallel, or a pulley system could be used. This is a picture of the launcher with the listed components from the side view and here from the above view. Then this is the launcher. Design decisions. All measurements will be converted into standard American units, and the desired output is a correlation between force and distance. Safety is essential, and maintaining safety to the researchers is a priority. The design objectivity will be, the design matrix is as follows. And all of the design possibilities were evaluated based on this matrix, and that's what we used to decide what we would and wouldn't have in the launcher. These are the references.
Are we doing any hands? Gracias, Robert.
I'm down for that.
Gracias, Robert.
Yeah, left hand.
All right.
Someone do it the other way.
All right.
Okay.
Uno, dos, tres.
Gracias, Robert.
That's so